Hello class, this is Mrs. Ayodeji with today's video on 13.2, defining functions using sums, arithmetic series. As you're watching the video, please feel free to pause, rewind, or replay the video as often as you need so you can get a clear understanding of what is occurring. Please write down important vocabulary, formulas, equations in your notes and bring those notes to class. And at the conclusion of watching the video, write a brief summary and submit that summary via the online WISC the day before class. Okay, let's begin. Today we're going to be talking about summing, and it's important to introduce the summing notation chosen using the Greek alphabet of sigma. And sigma has three parts. The bottom part, which indicates the beginning term value that we're starting our sum with, and the top part ending the ending term that we're ending our sum with, and then K representing the formula to calculate each individual part that we're using to sum up. In this case, this represents summing the numbers from 1 to 5 because as K equals 1, and then K equals 2, and then K equals 3, and K equals 4, then K equals 5. Okay, very simple, and we've talked about this in class, and you've probably seen it before. Today we're going to talk about an arithmetic series, and by definition, an arithmetic series is the sum of the terms of an arithmetic sequence. Okay, so the sum of the terms of an arithmetic sequence is called an arithmetic series, and this sum represents one number, where this represents a collection of sums, which is also a sequence. But we're going to focus on right here the S sub n, and the reason why we're focusing on S sub n is because well, you'll see a little bit later. So I want to point out that when we talk about an arithmetic series, it's arithmetic and not just a regular series. It's because of the fact that it sums the terms of an arithmetic sequence. And in the next video, we'll look at a geometric series, which sums the terms of a geometric sequence. But in this video, we're only talking about summing the terms of an arithmetic sequence. And as you can see here, we're relating the sigma notation we talked about earlier. We start with the first term, A1, and go all the way up to the nth term, A sub n. So this notation represents the exact same thing as S sub n, which is the sum of the arithmetic sequence terms from 1 to n, which is another way of looking at this. Okay? And using the same notation, this is exactly what it means. So in this case, S100, based off of the original value expression up here, represents the sum of the values from 1 to 100, which actually equals 5,050. In an interesting story, it is quoted about the famous mathematician Gauss. When he was a little boy, he was getting on his teacher's nerves, I guess because he had finished his math work and was talking to others, I don't know. And so his teacher, in desperation, just told him to go stand in the corner and count the numbers up from 1 to 100. And he came back moments later with the answer, and she was shocked. And it just indicated his, mathematical genius. Well, some people suppose that the reason why he was able to come up with the correct answer so quickly is because he noticed a pattern, and instead of adding up each of those numbers, he was able to take use of the pattern. So let's take a look at this pattern. The numbers from 1 to 100. They really are a combination of 50 pairs of the sum of the number 1 and 100, because 1 plus 100 is 101, 2 plus 99 is 101, 3 plus 98 would be 101 as well, and there are 50 of those, and that's what they suppose Gauss used to be able to figure out his answer quickly. And so all he had to do was multiply the number 50, since there are 50 of those pairs, times 101 to get his answer. So we're going to look at the math behind that explanation. So first, let's consider that S sub n represents the sum of the numbers from 1 to n. And it looks very much something like this. And that if we were to add these numbers, we end up with a bunch of combinations of 1 and n. Why do you say that? Well, 1 plus n, the first and the last. 2 plus n minus 1, when I simplify it, that also becomes 1 plus n. And 3 plus n minus 2 also becomes 1 plus n. So we're going to basically have half of, since we're using each of the n numbers is going to be used in a pair, we're going to have n over 2 pairs of 1 plus n. And so we end up with this expression to represent the sum of the numbers from 1 to n. And I know some of you may be saying, well, what if our arithmetic sequence is not just the numbers from 1 to n? What if it's a different arithmetic sequence? And I'm ahead of you. So let's suppose a sub n is not the sum of the numbers from 1 to n. A sub n is not the sequence of numbers from 1, 2, 3, 4, 5, 6, 7, 8, whatever. It's just a general sequence. So that means the partial sum, s sub n, is equal to a1 plus a sub 2 all the way up to a sub n. Well, let's take a look at the pattern. Let's take a look at the first and the last, which is a1 plus an. Let's take a look at the second and the second to last. Okay, and let's look at the third and the third to the last. And what does that equal? Well, let's rearrange some things to get a better idea. Well, first of all, how many of these pairs will we get? We talked about earlier, since we're pairing up two numbers at a time, it's going to be half of n pairs. And for right now, we're assuming that n is even. You have an example in the GEA where n is not even. We'll talk about that later in class. So let's take a look at this. Well, a1 plus an, just looking at this one right here, is equal to a1 plus n minus 1d. If you guys remember, that represents a2 since this is an arithmetic sequence. So when I simplify terms, I get two a1s, as you can see here, plus an n minus 1 times d. Okay, let's take a look at a2 plus a n minus 1, the second, oops, wrong color. Well, a2, we already said before, was a1 plus the first common difference, and a sub n minus 1 is a1 plus n minus 2 times a common difference. And so when we take a look at this, we still have two a1s, and we have a d plus an n minus 2d, which ends up being just n minus 1d as well. And if we continue along that pattern, we see that we're really going to have 1/2 over n, 1/2 times n pairs of 2a1 plus n minus 1 times d. And so that's another way that we can use to determine our formula for just any general arithmetic sequence, as long as we know the closed form formula for the arithmetic sequence. And this is what we have right here. Either of these will work. This is my favorite because all you got to do is just take the first term and the last term and add them together, and then multiply times n and divide by 2. But sometimes you don't always have the last term, and you only have the first term and the common difference, and of course n, and then you would use this formula, which comes from here. All right. So I encourage you to do some practice problems and get familiar with the terminology. See you in class.